So I'm happy to report that I finally got the videos posted. I'm not sure the audio stereo issue is solved yet, but I did get 2 videos posted. I got 2 sets of highlights posted, and I will get MP3s of those. You can make your own MP3s if you want, but I will post some MP3s shortly as well. So I'm finally caught up on video, and I will try to stay on top of that the rest of the term, which is good. Being behind with the videos is no fun. All right, so today we're going to spend a fair amount of time talking about buffers. I'm going to talk about an equation, and today is where that thing I described earlier about practical ways of doing mathematics I'm going to present to you. So I hope this will all be helpful to you and will make some sense. So last time as I got talking, I showed you this equation at the very top. And this equation at the very top is the one that you're just going to ignore. And you shouldn't. Okay? You shouldn't ignore this, because I sit down and students will say, oh, I don't understand this problem. I say, okay, well, we've got a buffer. Let's think about what's happening. And so I ask them where they would start, and they never start with this equation. Okay? So my advice is when you start working with buffers, the very first thing you want to do is you want to write down this equation to remind you what's going on with a buffer. Okay? Because this is really important. There are 2 terms on here that we want to start with, acid and salt. Okay? The acid on the left, as I described to you before, is a weak acid. Okay? HCl is a strong acid. They're not the same thing. Okay? So a weak acid makes up a buffer. A strong acid will not make up a buffer. It will not act like a buffer. You put a strong acid in solution, all the protons come loose. The pH drastically changes if you don't do anything else. Okay? Put a weak acid in solution, and you got some ability to help modulate changes in pH. And that's what a buffer does. It resists change in pH. Very, very important consideration. Okay. Now, some people look over here and say, oh, that's a conjugate acid, conjugate base, blah, 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 and they make you memorize all these terms, and we're not going to do that. We're going to use 2 terms in this class. The term acid, weak acid, will refer to a molecule that has 1 more proton than a salt. Okay? So we have 2 things, weak acid and salt. Weak acid has 1 more proton than a salt does. You should always be able to figure out which one is the salt and which one is the acid in any given equation, because the acid will always have 1 more proton than the salt will. Okay, we start with that. We're not going to call this base because it will confuse you if we do. Everybody clear on that? Okay. Now, I told you yesterday at the very end of class that let's imagine we had a situation where I had 500,000 molecules of this and had 500,000 molecules of this sitting there in solution, and I dumped in a bunch of protons. I told you that weak acids or salts in this case, have the ability to absorb protons, because this equation tells us if we go to the left, that if we add protons to it, this is going to move leftwards, and if we take protons away, it's going to move to the right. So if I have something gobbling up protons and taking them away, this guy is going to start trying to replace them. That's a very cool thing about a weak acid. The salt of a weak acid can accept protons if they get dumped in excess, and the weak acid itself can replace protons if something is taking them away. Now, what does this mean? Well, let's say I've got that situation where I've got 500,000 of these, I've got 500,000 of these, and I dump in 10,000 protons. How would I dump in 10,000 protons? Very easily. If I dump in 10,000 HCl's, I know that it will immediately come apart as 10,000 protons, because strong acids completely come apart. Okay? So I dump in 10,000 HCl's, they come apart, 10,000 protons come off, and I said for a microsecond those 10,000 protons are there, but what's going to happen is this guy's going to go, oh wow, excess protons, we're going to move to the left, and in fact, most of those protons are going to get gobbled up. We'll therefore have 510,000 of these guys. We're going to have 490,000 of these guys. Very simple. How would I take protons away? Well, I would add a strong base. Now, I'm hoping that you're guessing from what a strong acid is. You could tell me what a strong base is. Sodium hydroxide is a strong base. You put it into water, it completely comes apart. You put 5 million NaOHs in water, you get 5 million NAs and 5 million OHs. Well, what do OHs do? They combine with protons and make water. If I put in 10,000 NaOHs into here, what's going to happen is I'm going to have 10,000 of those OHs that are going to form, and they're going to start pulling protons away. And as they start pulling protons away, this is going to start replacing them. So now I've done the other situation. Instead of having 500,000 and 500,000, I've taken 10,000 protons away. I now have 510,000 salts, and I have 490,000 acids left over. So it's very important you see what's going on here. I'm altering the amount of acid and salt by adding a strong acid or a strong base. And there's a one-to-one relationship. For every one proton I add, I move to the left. And for every one proton I take away, I move to the right. Notice that one of these gets converted into one of these. Now, this is very critical to understand how a buffer works. Okay? I'm going to say more about buffers in a little bit, but this is the most fundamental aspect of buffers. Questions about what I've just told you? You're stunned in silence. You are so amazed at how simple that was that you can't imagine a question. Am I correct in that? No? People are nervously smiling and laughing. He's not going to ask me a question about this, is he? Because if I don't ask a question, he must assume that I know it then, right? And then the other thing that happens, it's funny being up here as an instructor, is people quit looking you in the eye because they know if he looks me in the eye that he's going to ask me a question, so, right? Okay. You can always tell when people are nervous, all right? It's really easy to tell because they will quit looking you in the eye. All of a sudden, the eye contact you have with the crowd just goes away. Oh, where's that fly over there, right? All right, questions? Yes?
But in reality, is always the reactions going this way?
Nope. It goes that way if I take away protons. It goes this way if I add protons.
But we see a lot of participations of salt in environments and...
Okay, so let's not confuse the term salt with sodium chloride. Okay? So a salt of an acid is something that is capable of accepting protons. Sodium chloride is not capable of accepting protons. Okay? So don't confuse a salt with the salt of an acid. Okay? Does that make sense? Okay. All right. Well, let's move to an equation because you guys love equations, right? All right. We're going to have a practical equation. All right? The practical equation we're going to have in this class is over here. All right? pH equals pKa plus log of salt, the concentration of salt, divided by the concentration of the weak acid. Now, we're going to have real practical things for this. This is where the practical mathematics comes in. In most classes, what that's going to be for you is an equation for you to memorize and probably try to futz it with a calculator, and that would be the end of it, right? We're not going to do that. We are not going to do that. First of all, you're not going to memorize the equation because I'm going to give you the equation on the exam. You're going to have to know how to use this equation, and you're not going to need a calculator, although you'll have one if you want one. Okay? Now, what does this mean? pH equals pKa plus log of salt over acid. You know what pH is. What's pH a measure of? Hydrogen ion concentration. Okay? It's the negative log of the hydrogen ion concentration, right? You know what salt is. Salt was that thing that was made up there. You know what weak acid is. That was the thing that was made in the other direction. What I haven't told you about is what's pKa. Okay? So pKa turns out to be something very, 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 very simple. It's a constant. It's a constant for a given acid. Each weak acid will have its own pKa, but for any given acid, that value will be a constant. I'll give you some examples. Acetic acid. I told you I would tell you more about acetic acid. Acetic acid is a weak acid. It has a pKa value of 4.76. No, you won't have to memorize any of these numbers either, because I'll give them to you as well, if you need them. Okay? 4.76. Formic acid is another weak acid. It has a pKa value of 3.75. What do these things mean, Kevin? What is a pKa value a measure of? A pKa is a measure of how strong a weak acid actually is. So there are degrees of strength of a weak acid. Degrees of strength of a weak acid. Some weak acids are stronger than others. Some weak acids are weaker than others. Okay? So I just gave you an example of formic acid with 3.75, acetic acid with 4.76, and you might say, which one is stronger? The answer is the one that is stronger will always be the one with the lower value. Formic acid is a stronger weak acid than acetic acid. Yes, sir?
Is the pKa of a strong acid theoretically the pH then?
There is no pKa associated with a strong acid, so we will not use that term. pKa, whenever you hear the term pKa, the first thing that should pop into your mind is we are not talking about a strong acid. Okay? Now, so this is a constant. What does this tell us? It tells us that the pH will change in a weak acid solution as the salt and acid concentrations change. Right? Because as these values change, this log term will change, and therefore the pH will change. And since this is a constant, it's not doing anything but just sitting there. Right? All right. Well, how does this change happen? Well, let's do it very simply. Okay? Let's imagine that we start increasing the amount of salt over here. We increase salt, we decrease acid. What's going to happen to the value of the log term? Is it going to go up? Is it going to go down? It's going to go up. So if I start increasing the amount of salt, what's going to happen to the pH? It's going to go up, right? Nice try, but
From the first formula, when I reduce the numbers of the H by adding more salt, this will increase the number of pH. That means hydrogen ion will be higher.
okay. So as I increase the amount of salt, okay, the pH is going to go up. The hydrogen ion concentration is not going to go up. Hydrogen ion concentration is going to go down. That's what happens when pH goes up. When pH goes up, hydrogen ion concentration goes down. They're opposite. Okay? Okay, that's fine. That's good. I'd much rather have you participate and be wrong than just sit there and go, quit looking at me. Right? I don't like that. All right. So we've decided then that if the salt concentration goes up, the acid concentration goes down, the pH is going to go up. Right? The opposite is if the salt concentration starts going down and the acid concentration starts going up, you can pretty well figure out that the pH is going to go down. Right? Okay, that's good. Well, this sort of makes sense. Sort of makes sense. Why does it sort of make sense? Well, let's go back to our equation. Right? If I put protons into solution, what did I say was going to happen to that equation? What was going to happen to that equation? Going to move to the left, right? Going to move that way. So that means I'm going to start making an HA, right? And I'm going to start decreasing A minus, right? When I decrease A minus and I increase HA, what happens to pH? It goes down. When I add protons to a solution, what happens to pH? It goes down. You said, but a buffer resists change in pH. Resists is not the same as stops it completely. The pH goes down, but not very much. Okay? On the other hand, if I start taking protons away, I start making A minus, I start destroying HA, which means this term gets bigger, which means the pH goes up, and of course you know when you add OH to a solution, the pH is going to go up. Makes sense. Practical. Has anybody used a calculator yet? No. Right? You figured out what happened with this without using a calculator. No numbers, no crunching. You saw what happened. The equation told you what's going on. Let's do some numbers. And we're going to do numbers without a calculator. You're going to love that, right? Numbers without a calculator. Well, let's start with the situation I had before. The situation I had before was, I said, well, let's say we got 500,000 of these, and we got 500,000 of these. And we've got acetic acid. I'd like you to tell me what the pH is, and no, you can't use your calculator. We're going to do it in our heads. Very simple. All right, what is it? Well, the pH is equal to a constant. In this case, it's 4.76, because it's acetic acid. It's always a constant for acetic acid, right? Plus the log of 500,000 divided by 500,000. What is 500,000 over 500,000? 1. What is the log of 1? 0. What is the pH? 4.76. You're doing it. Okay? Let's imagine I've got a situation where I have twice as much salt as acid. pH going to be higher or lower than the pKa value? I hear higher. Do I hear lower?
You have more salt.
I got more salt.
Yeah.
All right. Whenever this log term is greater than 1, the log term will be positive. And yes, I'll even put this on a calculator, on an exam for you. When the value of that ratio is greater than 1, the log term will be positive. That's telling you in another way what I told you earlier, and you guys figured out, right? When this value of this ratio is less than 1, that means we have more HA than we have A minus, the log term is negative. That's going to decrease the pH value. Okay? Now, if you understand all of that, you will understand everything you need to know about Henderson-Hasselbalch for the first exam. Okay? Practical things that you understand as a result of this equation and this equation to tell you what's going on in that solution. Okay? Let's say I told you that the pH of a solution was 6 and the pKa of the buffer was 5. What would you tell me about A minus and HA? There's more salt than acid. Right? And if I told you that the pH of an acetic acid solution was 2 and the pKa of an acetic acid solution was 4.76, what would you tell me? There's more acid than salt. This ratio will be less than 1. Duh. You got it. Now, you didn't get lost. You didn't mispunch the number in your calculator. You told me what was happening in that solution using 2 equations. That's cool. That's really cool. Questions about this? Otherwise, I may just give you a pop quiz. Now everybody's going to laugh. There we go. So there we go. Very.
Could you go back and repeat or give us an example again of the pH and the pKa with no?
Okay. So let's say I have a solution that has a pH of 7, and the salt is greater than the acid. What can you tell me about the pKa? Is the pKa greater than or less than 7? I hear 2 less thans. Do I hear any greater thans? It's got to be less than. Why? Well, if this is greater, that means that the log term has got to be positive. So if this is 7, this must be less than that because I'm adding something positive to it to get that. Okay? That help? Calculations aren't bad, guys. You didn't need a calculator. You're welcome to have one, but you really didn't need a calculator for that. Calculators lead you into trouble. Okay? Okay. Well, let's think about buffers in a little different way. Okay? This is cool. All right? The Henderson-Hasselbalch equation, there it is. pH equals pKa plus the log concentration of salt divided by log of concentration of the acid. Very simple. Okay? The Henderson-Hasselbalch equation you're going to hear a lot about. I'll talk more about it as we get going along. Here are some various weak acids. No, you're not going to memorize this table. All right? Some various weak acids that we find in living cells. Okay? You see the acid, the HA, you see the A minus, and you see the pKa value. You look at some of these and you say, whoa, hold on here, Ahern. Oxalic acid, you've got 1, you've got 2, and they each have their own pKa value. Can everybody figure out what's going on with this? What this means is this guy has 2 different groups that can ionize, one on the left and one on the right. Each of these acts as a weak acid, and each of these will have their own pKa value. The loss of the first proton is associated with a pKa value of 1.23. The loss of the second proton has a pKa value of 4.19. Okay? Now, we'll see this with amino acids. All amino acids have at least 2 pKa values. And no, you're not going to memorize the values, but I'll show you what happens with this. Look at this. Here's the acid. Proton, proton, right? Here's the salt. Proton, no proton. It's got one more proton, right? Look at down here. This same guy is the acid over here because it's got one more proton than the salt does over there. Okay? So the acid is always something that's got one more proton than the salt. Relative to that one, this one's the acid. Relative to that one, this one is the acid. Okay. Well, we see quite a wide variety of these. If we scroll all the way down, which I don't think this is going to let me do, let me get my, hold on here. My thing is running off the bottom and I can't rescue it. There it is. Okay. If we look at the very bottom of that, you can see that phosphoric acid actually has 3 protons that can come off. And there are a few amino acids that also have 3 protons that can come off. All right? We'll talk about those in a bit. And we see quite a wide range of pKa values. Which of these is the strongest acid? Which one? The first one, because the lowest pKa value will be the strongest of the weak acids, right? This will be the weakest of the weak acids. All right, good, good. You guys are getting it. Okay. Why do we worry about pH? Well, pH turns out to be really critical when we're talking about things happening inside of cells. The reason that your finger burns when you get that HCl on there that I mentioned yesterday is because you're damaging nerve cells. Okay? Our body, our blood has a pH of about 7.4. We have buffers that hold it in that range because if we get very far away from 7.4, we start damaging proteins. Now, damaging is used in a very loose sense here because damage to proteins basically means that we alter their shape and their function. Okay? That's what this graph is showing us. Here are 2 enzymes. Enzymes are proteins that catalyze reactions. We'll talk a lot more about enzymes in the future. Okay? Enzymes are proteins that catalyze reactions. We are plotting the relative activity, that is how active the enzyme is, against the pH. And we see, whoa, these guys have optimal pH ranges in which they exist. Most of the enzymes in our body function in a range around 6 to 8, somewhere in there. Trypsin's about 6. Optimal activity right here. We get too far out here, very little activity. Very little activity. What the heck's with this guy? What's that?
Digestive enzyme.
Digestive enzyme. It is in the acid of your stomach, and it's really set up well there. Okay? But if we get outside of its normal pH range, it doesn't work worth a crap. Okay? So, it's important that we maintain a relatively constant pH for our cells and the proteins within them, because if we don't, we're going to lose that function and the cell's going to die. Okay? We'll talk a lot more about protein structure in a bit, but this is the first indication of the importance of pH relative to protein structure. Okay? All right. How many of you guys did freshman chemistry and you had to do a titration? Oh, isn't that fun? My God, it's never going to change. It's never going to change. Drop, 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 drop. And all of a sudden it goes boing, right? You guys have done those, right? All right. So in a titration, we are plotting pH versus, in this case, and in fact in this class, we'll always be adding OH. What does OH do to a solution? Takes away protons, right? What's going to happen to the pH if I add OH to a solution? Going to go up. Why does it go up? Well, I'm taking away the protons, that's right. But relative to our equation, what's happening there? I'm taking away protons. When I take away protons, what am I losing? Losing HA, that's right. And making A minus. That ratio gets bigger. pH is going to go up. That's why it happens. All right. Very good, very good. Well, this is a plot of the pH within what's called the buffering region for acetic acid. Notice I said a buffering region. Buffers don't resist pH at all pHs. They're only effective within a pH range of about 2. 1 pH unit below the pKa value and 1 pH unit above the pKa value. Why do you suppose that's the case? Well, let's go back to our equation. Let's go back to our equation. We're going to use a little practical mathematics here. And here we are. Okay? 1 pH unit below, 1 pH unit above. All right? Well, 1 pH unit above corresponds to a 10-to-1 ratio. To make the log term increase by 1, I've got to have this guy increase by a value of 10. I no longer have 500,000 and 500,000. I've now got 900,000 of these, and I've only, or 900,000, and I've only got about 90,000 of these. I don't have too many of these guys over here that can donate protons. They're not going to be as able to resist a change in pH as if they were equal amounts. Does that make sense? Equal amounts, I've got 500,000, I've got 500,000, I've got a lot of capacity to add or subtract protons. When I've only got 90,000 of these and I've got 900,000 of these, I don't have much capacity to replace lost protons. Right? If I do it the other way, I've got 90,000 of these and I've got 900,000 of these, I got the same problem. So if I get this ratio too big or too small, I'm not going to be able to resist the change in pH very well. That is actually what's going on in a titration curve. All right? This is drawn in sort of a bad way, I will be honest with you, but you'll notice it's fairly flat, meaning it's not changing in pH very much over a fairly wide range, but once I get to within about a pH unit, it's going to go boing straight down. And this guy's going to go boing straight up. Because there's not going to be much to resist the taking away of protons, or in this case, the addition of protons. Okay? So, we will say that a buffer has maximum capacity to resist pH when the pH equals the pKa. Buffer has maximum ability to resist a change in pH when the pH equals the pKa. We will say that the buffering range for a buffer goes from 1 pH unit below the pKa to 1 pH unit above the pKa. Okay? Everybody with me? All right. Now, we see what's going on with buffers. All right? Here's a little bit more dramatic of a titration curve. This shows a phosphoric acid. Here is the acid. Here is the salt. We see that within about a pH unit above or below, from 6.2 to 8.2, this curve is fairly flat. We get outside that range, boing, it goes down, boing, it goes up. pH is rising a lot with a very little change in hydroxide. pH is changing a lot in a very minor change of hydroxide. But within this range, when I add hydroxide, it doesn't affect things much because we are in the buffering range. Okay? Very cool. Okay. You don't need to memorize this. I'm just showing you this. Okay? Just to illustrate for you what the ratio of that salt to acid corresponds to. If the pH is 3 units below the pKa, there's 1,000 times as much salt as there is acid. The pH unit is 2 units below, there's 100 times as much, I say salt is acid, there's 100 times as much acid as there is salt. Sorry, 100 times as much acid as there is salt. Okay? 1,000 times as much acid as there is salt. Down here, when the pH is 3 units above the pKa, we have 1,000 times as much salt as we have acid. Okay? So, when we're close to this 1-to-1 ratio, somewhere in this range, we've got pretty good ability to resist changes in pH. Out in these ranges out here, we have virtually no ability to resist a change in pH. Very, very little ability to do that. Okay. That's very cool. Okay. Now, I have 2 more things. I'm actually going to finish early today because I've got to be somewhere else again tonight, so you guys are going to get off easy. I want to say a couple things. So first of all, I'll take any questions. Are there any questions about what I've been saying to you? Anything you'd like to see again? Yeah?
Does the titration curve look different if you add equivalents of HCl instead of NaOH?
Oh, good question. Does the curve look different if I add HCl instead of hydroxide? What do you guys think? What do you think? Well, the only thing that would be different would be our starting point. So when we start adding HCl, we're going to have to start with something that has no proton on there. And that means our curve is actually going to be, it's going to come down, and then it's going to go like that. So it's going to be sort of a reflection of what we currently have. And to keep from confusing you, in this class, I will always add OH. We're always going to be pulling the proton off in that direction like so. That keeps it simple, and it keeps it consistent for what's going on inside of the buffer. A good question. Good question. Yes?
This might be a little off topic, but say you were like shooting for a certain pH, could you use like multiple buffers to kind of like...
Oh boy, good question. So what happens if you got more than one buffer in solution is basically what your question is about. Okay? So multiple buffers become very complicated mathematically to solve. Okay? Do multiple buffers give you a wider range of pH to protect against? They do. They do. Okay? Our body is pretty full of buffers. The carbonic acid buffer that we have, we'll talk about later, is based on carbon dioxide. And it's a fairly complicated buffer, but it helps keep our blood pH at around 7.4. Okay? So yes, it does get very complicated, and so we won't do that in this class. But the fact of the matter is that more than one buffer with more than one pKa value, which is what you have with that, does give additional buffering capacity. What do you suppose is going to determine buffering capacity? I say capacity. I've been throwing this term out there. What does that mean? If I said to you, what's the capacity of a buffer, what would you tell me? Range of resistance. What does the range of resistance mean?
It would be when that pKa equal to the pH.
Well, so that will be true for any buffer. Now I'm thinking, what's capacity mean?
It's different from an acid and another acid.
Not quite. You're confusing that with pKa. Okay?
The maximum change that the system can withstand.
Okay. So the maximum change the system can withstand. Go a little bit further with that.
So, for
Yeah,
example,
it's related to what she's saying over here.
so if you have a system with a certain buffer capacity, you can start adding protons or hydroxides up to a certain level, and once it gets beyond that buffer capacity, it's going to, like in the graph, it's going to shoot up.
Okay, so what he said is right, okay? So the buffer capacity is really how many protons can it handle before the pH goes wacko, right? If I put it in non-scientific terms. How many protons can the buffer handle before the pH I get out of the buffering range, right? Now, you said, well, it's within that pH, that one pH unit, but there's another variable that's here. Okay? Let's say I have 2 solutions of acetic acid. And I tell you one has a greater buffering capacity than the other one does. Yeah?
It's related to the equivalence. It's the molarity of the solution.
It's the molarity of the solution. The concentration of the buffer will determine the capacity. The more concentrated the buffer is, the more ability it's going to have to resist the change in pH. And the less concentrated it is, the less capacity it's going to have. Exactly right. Okay? Make sense? Okay. What else should I say here? Other questions? Okay. Well, I'm not going to say it today, but I'm going to tell you one brief thing. Okay? What do you suppose this guy would look like if we were to take, because I told you before, phosphoric acid has 3 buffering points. What do you suppose its titration curve is going to look like? Is it going to look like this? Yeah. So what it's going to do is it's going to look something like this. pH, okay, OH added. It's going to go up, it's going to flatten, it's going to go up, it's going to flatten, it's going to go up, it's going to go flatten, and then it's going to go up. All right? That's what's going to happen. Now, what I've just drawn for you on the screen and what people out in TV land may or may not be seeing, I'll describe. Up, flat, up, flat, up, flat, up, right? Okay? What I've just described to you in terms of a titration plot is exactly what many amino acids are going to look like. Because they've got more than one proton that can come off, and each group will have its own characteristic pKa value. Now I want to say one more thing about pKa, and then we'll do a song to finish the day. Okay? I know that'll break your heart. Okay? Another thing we say about pKa is that pKa is the pH at which salt equals acid. We've already shown you that in the equation before. pKa is a pH at which the salt equals the acid. pKa is the pH at which we have maximum buffering capacity because the salt equals the acid. Okay?
Does how electronegative the buffer affect its ability to buffer?
So does electronegativity affect the buffer is the question. Electronegativity affects the ionization of a molecule. So when we look at HCl, there's a big difference in the ionization of those, the electronegativity. Chlorine has a very high electronegativity and completely takes the electron away. So it ionizes. And so that's why when you put it in solution, it completely disappears. That the proton completely goes away. There's not a sharing as such. It's gone. So electronegativity affects that whether it's a strong acid or not. It doesn't have a big effect, for our purposes at least, on whether it's a weak acid. Okay? Okay. You guys up for a song? All right. I have a song to drive all this home for you. Actually, I'll do it over here. You got to sing loud. It's to the tune of My Country 'Tis of Thee. It's called Henderson-Hasselbalch, okay? Henderson-Hasselbalch, you put my brain in shock. Oh, woe is me. The pKa's can make me lie in bed awake. They really give me bad headaches. Oh, hear my plea. Salt-acid ratios help keep the pH froze by buffering. They show tenacity, complete audacity, if used within capacity to maintain things. I know when H's fly, a buffer will defy them actively. Those protons cannot waltz when they get bound to salts. With this the change in pH halts. All praise to thee. Thus now that I've addressed this topic for the test, I've got know-how. The pH I can say equals the pKa installed with some of S or A. I know it now. All right, guys.